at some point, even when I'm increasing the substrate concentration to infinity, this just slowly approximates to going a little bit faster, but hardly at all. Why might that be possible? Tell somebody else if you think that. Oh, go ahead. I think you got it. Go for it.
All the sites are taken up, right?
Yeah, so if all the sites are occupied, even though it's doing a reaction and going product, but they're always essentially occupied, then more substrate's not helping. I'm ready to load as soon as you're done, right? I'm just right in line. We got backed up lines just saying, come on enzyme, do your job. That's what we're describing. And so that's the Vmax. At 1/2 Vmax, we went to the math and that defined also a way to actually theoretically, right off your data, find the Km. So that's useful for us because the Michaelis-Menten equation, that just gave us the overall rate constant for it, okay? And these are velocities on this axis, this is substrate, and what you see drawn here, and there's Michaelis-Menten equation, what you see drawn here, you will need to regurgitate exactly what you see up on the exam, okay? So that's reasonable. You don't need to put the millimolar or micromolar per minute, but it is a concentration per minute, right? That's what a rate is. Now, to make that plot, this is what some people got a chance to do in lab just the other day, and it's pretty fun. So you look at this and you start collecting, let's just look at one line, okay? We're down here, we start collecting data, we've got our enzyme, and it's producing product. We're gonna assume that the product is a colored product, and so over time you see it increase in concentration and that color starts showing up. Why is it slowing down? Why is the...
Because you're using up your substrate.
Yeah, I'm not making more, because I used up the substrate. I'm running out of gas, okay? So this slows down, but early on, and this is hard to see early on, but it's really clear later on when you go to higher substrate concentrations, this line appears to go straight for a good ways, and then it slows down. That's about steady state approximation. It's slow, when it's right here in this linear region, that's when steady state's happening. Which is when essentially I've got just even flow of pull it in or let it go again, or pull it in and go to product, and what's going backwards or to product is equal to what's coming and loading it, right? That is steady state. And that's linear. This product over time is the velocity, right? Mm-hmm. And though this looks like the plot we just looked at, these axes are very different, right? This is a hyperbolic plot, but I can read those lines off my data, and when I do, I get data points that look like those red dots. So each of those lines here, those slopes, is one data point that makes up what we plot for this curve. Okay, so then we have everything we're interested in. So does that make sense that as this substrate goes up to infinity, I essentially end up with something that just keeps going at the very same rate? Go ahead.
How do you get a data point from a slope?
So it's a rate. So I am going at 3 molecules created per second, or 20 molecules per second, or so many micromolar per minute or per second. Okay? Does that make sense? It is both data points. So it's the slope is the fraction, and it's got both of the values in it. Hence micromolar per minute. If I take this equation and I do the reciprocal of it, now that means mathematically I just divide everything by one divided by itself, right? Yeah. I actually can remanipulate this equation to be y equals mx plus b. You've seen that one before, right?
Yep.
So if I take 1 over substrate and 1 over the velocity, I end up with the plot that looks like this one, which is the Lineweaver-Burke you were told to peek at. And this is a linear plot. So in addition to drawing the hyperbolic plot, you'll also draw what's called the Lineweaver-Burke plot. And this is what it will look like. And you'll also label the axis here. The axis here being, this is the slope, which is Km over Vmax. This is 1 over the velocity. This is 1 over the substrate. This is 1 over the Km. This is 1 over the Vmax. This is actually negative 1 over Km. And don't forget the negative. So why is this better to read the Vmax than this one here?
You have an actual linear.
I have a linear line,
And you have an intersect.
and I have an intersection and I know exactly what it is. So I can actually get the Vmax, and I can get the Km, and reading those as exact values. So let's look at what that would look like in data, okay? We're gonna assume that you, the awesome class that I have, the student dose is going to produce product case, right? And so our student dose has got its millimolar concentration and your velocity of how much product and all that you're learning is in micromolars per second, okay? Pretty cool, okay? And so we could get this and see what result we were getting. But if we want to produce a Lineweaver-Burke plot from that data, see here, can you see where the Vmax is? Now, this is a good eyeball exercise, and there's one in the book, and there might be one on the exam, and there's one we'll practice as well, where we're practicing how to eyeball this type of information. So let's take a peek and say, where's the Vmax on this? Obviously, it must be the fastest it could go. Is it really 40 micromolar per second though?
No.
You can see it slowing down though, right? So do you think it's gonna get to 50? Maybe it's gonna get to 42, maybe 45. It's hard to know, right? We could use some more data points, maybe that would help us. And sometimes with the more data points, you can estimate it. And then from there, if I were assuming that I was interested in the Km, how would I get the Km here? Yeah.
Would you just look at where it increases the fastest between 2 and 4?
Right, so let's assume it was 50, that was my Vmax. So I would be looking for 1/2 of the Vmax would be about 25, so somewhere in there. And so it must be between 2 and 4, so something close to 3 millimolar. Let's see how that plots when we actually then do our reciprocal of that, right? And then we plot that information, nice linear plot, and then we look at this data point that says that the 1 over Vmax is 0.02. Now, how do I get the Vmax from that? Show your neighbor in your calculator how to take 0.02 and get the Vmax.
Oh, money.
It's not hard, right?
No, it's just math.
Was it pretty close to what we guessed?
Yeah.
Yeah, that's doable, right? And so that actually comes out to the 50 micromolar, and this comes out to 3.33 millimolar. We were a little off, but we could get better numbers with the intersection. Remember, this was negative, and we had to get rid of the negative there. So there's how we do this game, okay? Everybody feel like you could draw one of these Lineweaver-Burke plots, label the axis, understand what you're looking at? Because we've got to figure out how to use this in about 1 second. Okay? So there's a couple other terms we want to define. We talked about Vmax, we talked about Km. Let's also talk about Kcat. Kcat is actually defined as the Vmax divided by the enzyme total concentration. So that's whether it was bound or unbound, just the enzyme total concentration and whatever the Vmax is. And so that's essentially saying per enzyme, how fast is it going per enzyme for the turnover? And that's my turnover number. How many products are produced per enzyme per second?
So is that concentration of enzyme per time for the ET right there, or?
No, the Vmax is per time,
Okay.
but this is total enzyme.
Oh, okay, okay.
Okay. The Km, you already knew what that was, and we already know it defines the substrate's affinity. Turns out that if I also take the Kcat and divide it by the Km, so how fast it can go divided by the affinity for the substrate, this gives us something known as the specificity constant. And it's actually limited by diffusion. How fast can I exchange when I'm doing my reaction and put the next one on? So that's the limit. So the diffusion limit in a reaction, if I don't worry about loading it up, is about 10 to the 8th to 10 to the 9th per molar per second. Okay, that's just a number, okay? How well are our enzymes, these are real enzymes, how well are they getting to the diffusion controlled limit?
Pretty close.
They're almost as fast as you could possibly go. I mean, these are up in the 8th, 7th, these are fast, right? Enzymes are very capable of going fast. There's one known as Rubisco, which turns over 3 per second. It's the slowest one I know. It's also produced the most product on planet Earth. Rubisco is used to fix CO2 when you're actually doing photosynthesis.
Oh.
So all plants on Earth, any photosynthetic product. Yeah. Okay. We're gonna look at some Lineweaver-Burke plots. Most people who study for something like an MCAT or DAT take these and memorize the pattern, and it's good enough to pass it, and they're happy with it, but it means they understand nothing about kinetics. And I'm not saying that in a critical way, I'm just saying we're gonna look at a paper where we're gonna use that to understand what you're looking at. But I really want you to understand it. So there's, in a bi-substrate reaction with an enzyme where I have 2 different substrates I'm gonna put on, we have 2 versions, a sequential mechanism or a ping pong. You're interested in looking at these. We have random ordered and sequential, which are both sequential mechanisms. So this is ordered sequential and random ordered. What's the difference between them? Somebody can look at that and tell me.
One can bind either substrate 2 or 1 first, and it doesn't matter, it can still form products, whereas in order it needs to bind substrate 1 specifically first, then substrate 2.
Perfect, perfect. Now, the other one we have looks a lot like ordered sequential, and in truth, it is an ordered sequential reaction, but it doesn't look the same. It's called ping pong, it's also known as double displacement. We all like to name it ping pong because it's easier to remember in our brain. This one does something different than this one up here. This prime means that first I bind substrate 1, and then I actually do a reaction where product 1 leaves, and it leaves me the enzyme, but the enzyme's been modified in some way. It's changed. The easiest way to consider this is if I were taking something like ATP, and I'm breaking it up, so I now have ADP and inorganic phosphate, but I'm gonna keep the inorganic phosphate on my enzyme and let ADP float away as product 1. And now I'm a modified enzyme. It is at that point that I can bind substrate 2. So I couldn't bind substrate 2 till the reaction happened and the product left. But now I can bind substrate 2, and then I go off to product. Do you understand the difference between just ordered sequential now and ping pong or double displacement? Okay. So it's sort of a 2-step reaction. Okay. So when you look at these, go ahead.
I guess so the main thing about the ping pong is that the enzyme has to be changed by first
Yes.
reaction.
Yeah, and there's a product, an intermediate product. Yeah. So if you look at the ordered, which can be these are sequential, ordered or random, they both put this plot out. You actually can't look at the Lineweaver-Burke plot and know what's going on. But this is the first time you've seen a Lineweaver-Burke plot, and then you've seen another Lineweaver-Burke plot, another one, all plot on top of each other. What's happening in this plot, just so that you get the picture so you can get the rest of them with me, is let's assume we've got this first line right here. In order to get each data point on this line, what did I do? Remember that came from the hyperbolic plot. So you're really talking about what we just talked about today. In order to get each data point to get that reciprocal line, what did I do?
You measured at multiple concentrations.
At multiple concentrations, I've measured the
rates.
substrate,
Yeah.
but the enzyme concentration stayed the same. But this is a bisubstrate system. So I kept substrate 2 constant the entire time on this line.
Oh, okay.
But substrate 1 varied in concentration to give us the change. And then to do line 2, I increased substrate 2 concentration to a new level, but kept it constant throughout the entire line and altered substrate 1.
Okay.
Tell somebody else that you got what I said, because that's really hard to explain, right? I mean, hopefully you see it, but try to wet your chops on that. What did I just try to say?
Substrate 1 and enzymes are the same. Substrate 2
All right, are we there? Are most of us caught back up? Okay, that's hard to say, right? Okay, so this right here has this intersection line. This is also known as the ternary complex, and all we're really saying there is there's a point where if I'm varying substrate 1 along the axis and substrate 2 is at constant concentration, that at one line versus another substrate 2 concentration, another one, that there's a sweet spot where the rate actually becomes the same in all those lines. But the Vmax isn't the same, because let's face it, if I have more substrate 1 and more substrate 2, what's going to happen? I'm going to have a higher Vmax. That's right. So wait a second. This says substrate 2 is increasing and this value is going down.
Well, you have, that's a reciprocal.
But that's a reciprocal, which means it's 1 over. So that's actually increasing the Vmax. Uh-huh. Got it. Okay. Good. The ping pong we just looked at, remember that one had the intermediate product form? It forms parallel lines. Sweet. Easy to remember. Okay? This is the same way we made the line. Substrate 2 is increasing like this. This is kind of interesting here. As this happens, we have a change in Vmax, and the Vmax is getting higher. We would expect that. What's happening to the apparent Km? Is it getting smaller or is it getting bigger?
That's getting bigger though, because it's negative reciprocal.
It's the negative reciprocal. So it's hard to see this side. You sometimes can easily see this, but let's look at that really quick so we see it. Let's assume the first line is 1 over 4. This is 0.25. Okay, let's assume the next one over here is 1 over 2. And let's assume this is actually 3/4, 0.75. Okay? Now I do the reciprocal of this, and this would be 1.33, this would be 0.5, sorry, 2, and this would be 4, right? So I flip them over. So which one's the fastest Km? That's the rate constant, well, obviously the bigger number. And yes, these were negative, right? But we took the negative of that to get back to our 2 Km. Okay. So hopefully that makes sense on what you're looking at here. It also means that, obviously, if I increase K1's concentration and then I increase K2, it has the ability to go faster, but it actually goes faster linearly because I'm always waiting for the substrate 2. Yeah.
When you describe the graph's change, do you say it shifts right or does that shift down?
So substrate 2 is increasing, it's just moving down linearly. And so essentially the Km and the Vmax are increasing. And it's doing that because I get to the first point the same no matter what with substrate 1. And then when I finally have product formed, if I have more substrate 2, it goes faster. So it will move linearly.
So does this mean that, would we say that substrate 2 is rate limiting or something like that?
It's not necessarily the rate limiting, but it has the appearance of being rate limiting, right?
Okay. Because it's the one that's defining how fast you get to go.
Yep.
Okay.
Okay. All right. There's now the other side of it. That was just a bisubstrate system. Now we're going to look at an inhibitor and just a single substrate. What's an inhibitor? A toxin, a drug, something that slows the reaction down, okay? So there are different ways to have inhibitors. And so these names of these different inhibition methods, you need to know. And they sound very alike, and I didn't create the vocabulary. But somebody did, and they reveled in that to mock you, okay? So you get to learn them whether or not you like the names or not. The first one makes perfect sense to us. We're going to have the same Vmax, but an increase in what's known as the apparent Km. Now, what's happening is the enzyme reacts with the substrate, goes on to enzyme substrate and enzyme product. That's normal, right? But in this case, the inhibitor right here can also interact to make a complex. They're competing for the very same spot. The inhibitor and the substrate look alike. As a result, what happens if I bind the inhibitor to the rate?
You effectively reduce the amount of enzyme you have,
I have less enzyme around.
so it reacts slower.
But what happens to the substrate concentration for the enzyme that's left?
Oh.
It's a higher substrate concentration for the enzyme left, so it appears to be going faster even though it's not. And that's what was called an apparent Km. So, yep, sure enough, I'm increasing the inhibitor, and this is going bigger. Weird. But this is staying the same. How is that possible, that staying the same? We talked about it the other day. Go ahead. Yeah.
Oh, I was just gonna guess ratios.
Ratios? It is about ratios. Elaborate more.
Because if you're inhibiting if your inhibitor is acting like an enzyme and it's binding to your substrate, then those are now left gone, if you would. So then you have more available enzymes for your, or more
Okay.
substrates for your enzymes to work on. I don't know.
Somebody else want to help him out? Take another stab at it?
Hold on,
Well,
does this mean,
The Bmax is the same.
Well, I was just gonna say, if kind of what he's going off of, we think about the idea of like equilibrium, right?
Yeah.
We see that if the enzymes are being taken up by the inhibitor, it frees up more of the substrate concentration in the
Which is
initial-
why the apparent Km is getting bigger.
Right.
But the reason the Vmax is staying the same is at some insanely high ratio where I have so much substrate compared to my inhibitor, 1,000,000 to 1, maybe it's only 10,000 to 1.
it doesn't matter?
The enzyme only finds the substrate. It doesn't see the inhibitor. And so the Bmax appears to be the same. Yeah.
So in this one with this inhibitor, is this inhibitor binding to the enzyme and that's done, that's it? It's just bound
Okay,
and stuck, or is it?
we're not telling you whether it's a dead end inhibitor that's competing for the same site or whether it comes on and off. Okay? Either one would behave the same. It turns out that there's an equilibrium if it comes on and off, and there are issues with that. Okay? All right. So the next one that we have to talk about is known as uncompetitive, and we're going to pick up some speed here really quick, okay? Uncompetitive inhibition. Woo! We can handle it. It looks like that I'm going to bind the substrate, and then when the enzyme substrate complex is formed, I can either go to product or I can bind the inhibitor. So when can I bind the inhibitor?
After the first substrate.
Only after this enzyme and substrate are bound. So I have to do step 1 before step 2 can react. With that said, I have to do step 1 before step 2 can happen. Why does that look the same as the one we just looked at in a bi-substrate system?
It's ping pong.
This is not called ping pong. There's an inhibitor and there's a substrate. There's not two substrates, but they look the same, and they're doing it for the same reason.
It's because the concentration of the inhibitor is what affects how fast or how much it affects the overall rate.
Go ahead.
Because there's a second thing binding, whether or not that second
Yeah.
thing
Is determinant on what? The concentration of the substrate binding. So it's concentration of the substrate binding, and when it's done, it's only then that I can do the step 2. So concentration of the substrate 1 is directly proportional to how much enzyme substrate I will have that then I can attack with the inhibitor, or that I could attack with the substrate number 2. Does that make sense? If it doesn't, it will, or it will never, and you'll learn the pattern and memorize it, and kick out a lot of good answers and nice, happy, but you may not fully understand it, which would be a pain, because there's a paper we're gonna use it for. Okay, so that's called uncompetitive. So competitive, uncompetitive. Do you see these plots where I'm drawing this? You need to know this in addition to knowing its name and its pattern. The name, the pattern, and what it means is happening, okay? 3 things, okay? Be less concerned about this, even though it's cool that it happens. Just the pattern is good enough, okay? The last one we're going to talk about, and then we're actually going to talk about a special case of it that we'll use. This is called mixed inhibition. Mixed inhibition means that the inhibitor itself can bind first, but it's not going to the same site. It's not competing for the same site. I could also bind the substrate first. So either one's okay. The inhibitor's not going to the same site though as the substrate. So it turns out that I can also bind it after I've bound the substrate, or I can bind the inhibitor and then still bind the substrate, because both sites were available. But it's very probable that when I bind the substrate, it makes it easier to bind the inhibitor. But if I bind the inhibitor, it probably makes it harder to bind the substrate. These are all reversible arrows in the way they're drawn, which means the inhibitor could pop back off and I still go to product. These A's here I've been ignoring up till now, but they're just the activity constant that's associated with it. Meaning, how much does the shape of the enzyme change because I just bound this inhibitor to affect that then the substrate doesn't bind as well? Or I bound the substrate, how much does it change to make it more favorable to bind the inhibitor? Now it could go either way, by the way, but this is called mixed inhibition, And then there's a special case called non-competitive inhibitors we're gonna talk about. So mixed inhibition looks like this, and here's the plot. That looks a lot like what?
The first one.
Competitive inhibition.
Okay, it looks a lot, the competitive inhibition did what?
The
Where was
Vmax,
this?
the Vmax stayed the same.
The Vmax was the same on the line. This one looks more like sequential,
Oh.
Yeah.
right? But this is with an inhibitor. So you've got the plot, you've got the name, you've got what's going on. And if the alpha and alpha prime are the same, you end up with this plot. Which means that if I bound the inhibitor, it doesn't change the shape of the enzyme, so its binding of the substrate is equally as probable whether I just bind the substrate first or whether I bind the inhibitor first. If I bind the substrate first, it doesn't change the affinity for it to bind the inhibitor, it's just the same. So one's binding doesn't affect the other, but binding the inhibitor still slows the enzyme down. Okay? Both together are a product. And that's non-competitive inhibition, the last one you're looking at. Okay, ready to go fast? That was the confusing part. Don't freak out about it, learn all the patterns, be happy about it, we'll talk about it in the paper. Here's the next part. This isn't even part of this chapter. It's not on the exam. I'm just gonna show you there are factors that determine the activity of enzymes that we talk about. Yes, biochemists go all through receptors. Yes, we go through transcription factors and DNA. We go through mRNA degradation, ubiquination, which I find out that most of you don't know what ubiquination means. What's ubiquination? Say it?
Tagging?
Tagging a protein, marking it for
Destruction.
destruction. It's always good when somebody else makes me feel like you guys are enrolled in college. All right. You could also attach a regulatory protein, or you could phosphorylate your enzyme, or you could have a ligand that binds, not in the active site, but binds and changes the shape of it. Those are the ones we're interested in right now. Then, yeah, the substrate binding, or just sequestering the enzyme somewhere else. These are ways I could affect how fast the enzyme's working, and we deal with that metabolism because that's how we alter concentrations. Which, if I alter the K equilibrium concentrations, that has the ability to change an unfavorable Km, delta G, to a favorable one. Okay. The regulation could be non-covalent or covalent, and reversible or irreversible. Okay? Changing this, when I bind to my enzyme, an allosteric effector, we're talking about it going to another site that's not the active site, but it's changing the shape of the enzyme. Is it possible that binding an allosteric regulator could make the enzyme go faster?
Sure.
It changes the shape and the enzyme now actually can bind the substrate better and go to product faster? Yeah, it's totally possible. Is it possible to slow it down? Okay, so that's why they're describing positive or negative regulation. But what is this? This is velocity over K.5. What is K.5?
So that's the KD. No, that's not right.
One.
What was Km?
Km is approximately the KD.
Okay, it was, and where did we read it on a hyperbolic graph?
At
At 1/2
Vmax.
Vmax. It's the K.5, it's the 1/2. Why aren't they calling it the Km?
To make it harder
It's
to
the
remember.
apparent Km. I altered it by putting an allosteric regulator on, and now it behaves differently,
Okay.
either for positive or negative. So that's why they're changing. But it's still substrate concentration, it's still essentially a Km. Positive or negative. You should know that. There's green on there for a purpose. You should know that. K.5 always throws you for a loop, so we made a big deal out of it. Hopefully you don't forget. Sometimes we do feedback inhibition, meaning the actual allosteric effector could be the downstream product. Sometimes 3-4 steps down a pathway on a metabolic pathway, comes down and shuts it off. That's brilliant. It's like somebody says, I want to produce 1,000 cars today. And when I do, I want you to come back and tell me we've got 1,000. Your body can do that. God's smart. He's like, I got it. This is cool. How can we bind either reversible, covalent modification? What can we do? What's this?
It's a
Phosphorylation, very common in enzymes. Oh, wow. Phosphorylation. I could actually also put on acetyl groups. I could put on ribosylations. I could put on adenylations. There's a lot of ways to modify these enzymes. You don't need to know all these as much as know that I can modify proteins, which are enzymes by and large, right? And I can modify them with phosphates and sugars and lipids and also all sorts of other methyls and acetyl groups, and it will change their shape or their speed or turn them on or off. There are a special class of enzyme that actually themselves don't come out active. Now the ones I'm going to focus on when they don't come out active, but they're an enzyme, are known as the zymogen class. Why, if most of the proteases are zymogens, why would that be a good thing?
They're not working when you don't want them
Tell
to.
somebody else in your table. You're smart enough.
Shut them on and off when you need to.
Hey,
So like proteases.
Yeah, well, it's like digestive enzymes.
All the
You can
proteins,
release
most of the
them,
proteins.
and then you don't need, unless you need to shut them on to the they're always turned off.
I did watch the last.
I think that sounds great. We should start
We'll take
production
someone
tomorrow.
else. It's like a repeat, like a concise repeat of what I did before. So like it's not point. It's like so much better to do it. So you pause like.
That makes sense to everybody? I don't want a protein, an enzyme that comes out that its job is to chop up proteins coming out of my cell off the ribosome and say, let's go, I'm chopping up everything in this cell, you're down now. That's not great. So, trypsin comes out in inactive form. It's actually named trypsinogen in its zymogen form. This is named chymotrypsogen, zymogen, in its inactive form. Turns out that this guy, once activated, turns on this guy. And this guy is activated by peptidase. And that's good, okay? And then it works at a specific pH, and that's also good. So when this one gets activated, what happened here? This was initially 245 amino acids. Now what happened? I used a protease and I cut it.
Did you cut off a amino acid sequence? Is that what it's trying to tell
I
us?
cut off how many?
6.
6 of them. Now I got an isoleucine right there instead of the isoleucine at position 7.
Yeah.
Okay. What about when trypsin comes in and activates chymotrypsin at 245? What does it do? It cuts it right here. And
Another
that actually
isoleucine.
turns it on where the enzyme itself actually now comes in and also cuts itself. And now it's really going, okay? We will talk about this site when we talk about the chymotrypsin mechanism.
Is there a reason why it's isoleucines on both sides that you cut to?
So there's a reason that this is tyrosine,
Okay.
because chymotrypsin was active with which type of amino acids? We already covered that.
Aromatic.
Say it?
Aromatic.
Aromatics. And you're like, oh, there, that makes perfect sense. I'm going to cut to the side of the aromatic. And yes, there's a reason why it's isoleucine, but it's actually the arginine that matters.
Okay.
The isoleucine we'll talk about. But trypsin acts on arginines and lysines, positive groups.
Cool.
Which is great for my math stuff. Okay, you know what zymogens are? Are they used anywhere else? There's a lot of green on there. I didn't draw the green. It just comes out of the book that way. The green arrows mean on, the red means off. This is what's known as the clotting cascade. You want to go to medical school? You want to go to dental school? You want to go to pharmacy school? Good, you can memorize that. But I'm not making you memorize it. Oh, it's fun to learn. I don't have any problem learning it. But this is just zymogens that are getting activated, yeah.
I did have a question in regards to
Yeah.
the clotting cascade, because factor 8, factor 5 are also called cofactors at times.
Yep.
But they are also created from cofactors, or specifically vitamin K. So we have cofactors that are made from cofactors.
Yeah. Yeah, interesting, isn't it?
Okay.
And sometimes we call them cofactors because we get sloppy, but vitamin K is technically what type of a molecule, so we get the right use in our. It's fatty, it's carbohydrate. It's not a metal, right? So we should technically call it, even though old school versus new school, we should probably call it a coenzyme. But yeah, sometimes people get things wrong historically, and then the names stick. Which is why, by the way, you should know the difference so you can get right on the exam, but I don't know, carry on that. Because it's like messy. So, yeah, their ability to have that term, it's just saying that I can't have this enzyme working without this other coenzyme, but the coenzyme's not even available until it's made as part of the cascade. But that's a beautiful cascade, because it's saying, once this product's made, turn this one on. And sometimes start turning it off as part of the shutdown, okay? Feedback loops. So there's some awesome ones. Warfarin, Coumadin is known as what? Just because you need to be well-rounded in your world. Natalie, you had a question too, I didn't mean to. Warfarin, Coumadin, anybody know what that's about?
It inhibits vitamin K synthesis in the liver.
Yeah, it's essentially blocking. Okay, it's effective with blood clotting. Okay, it's rat poison. You feed it to rats, and what happens? They can't clot; they bleed to death.
Oh, really? Wow.
We feed it to humans too. They probably should have banned it a long time ago. My grandmother had a lot of Coumadin, warfarin, that she had to take because she had an enlarged heart and was at risk for heart attacks. They were trying to stop her blood from clotting, because if it did clot, then it would, with high blood pressure, cause a heart attack, a stroke, right? Depends on whether you hit the brain or where you're hitting the heart. Vitamin K is also responsible for clotting. We'll talk about vitamin K a little later. Let's just go forward and see if we're happy. Does this all make sense? And clotting cascade is just a factor where we essentially make everything a nice network, and then our molecules get sticky and we don't bleed to death. Yeah. Aspirin inhibits the cyclooxygenases, so it's inhibiting the
Part of the
blood. It's
cascade.
also stopping some of these, so that's where aspirin fits in. Other enzymes use it too. There you're looking at part of glycolysis, glycogen regulation, phosphorylation, turning it on. If you're looking at PKA, protein kinase A, all kinases add what type of a post-translational modification to the enzyme?
Phosphorylation.
Phosphorylation. So kinases are ones that phosphorylate. And they use ATP almost exclusively to do that. That was the first part. That was where we wanted to get to. Ironically, in the last 5 minutes, this is the other part that we had wanted to do with it. And it's already ready for you, so let me show you where you want to go. And I'll answer questions for the last bit of class, but I want you to realize that we can review this, and the answer key will be up for you. but you definitely wanna know this as an activity of what can you study at home in addition to the chymotrypsin mechanism when you're trying to understand, I gotta study stuff, I wonder if I understood anything good about it just said. Okay? So as a way to review this week, this little activity is designed for you. Where are we? We're in Unit 2, and you come along and you say, hey, I'm Unit 2, I want this Chapter 4 activity. Oh, I went to the wrong one, we're in Unit 3, sorry. Now I went all the
I remember that.
Sorry, you guys, something too slow. Our first activity for Unit 3. Not the one I was expecting. That's the paper we're gonna read. We'll have a good time with that. Where did I put that? I gotta go back. I know that I have it. but
And
I'm not
Professor
sure where.
Simon told us that he's not
Let
gonna
me
do
see if I can find that.
because he knew, that it was a.
This is
you
the
know,
activity right here.
and all of a sudden he's
Understanding.
like, yes, I went to
We
the
can't
store,
see it.
and he
Oh,
shot some
you wanna
mannequins
see it,
and
though.
shot my dog. He's like, my dog lives, so.
We have to do that.
Let me
all
go
the time
back.
with the clinic I work at. We buy the cake.
Unit 3,
And I was like, that's sick.
so right here, extra practice activity and
Just a little
understanding.
simple,
of
so it gets
activity.
to,
Wow.
gets the receptors. and-
This is what we're talking about.
And then.
Go to this. There's a link to understanding further mechanism, but this activity right here.
It's gonna have us plot it.
Huh, looks like what we just did in class. Could you just look at that and eyeball the Vmax? Maybe.
Kill him,
Could you determine the Vmax and Km from it? Okay, what if you then had the Vmax and Km, could you define the K cap?
Yes.
As long as I knew the concentration of the enzyme, but if I know that this is the concentration of the enzyme, but I need to know it's in molar, I'd have to use Dalton's. What is a Dalton?
AMU.
1, yeah, it's the weight of a proton, right? 1 AMU. Fine. Okay. So work through this. At the end of this, it has these plots right here where you're drawing energy diagram. We'll look at that on Monday, and we're gonna go forward. The answer key is also up there for you to click on, okay?
Oh, nice.
So,
Very thorough.
we're coming for questions. We're done with this part. We're going on to the second part, which is dealing with chymotrypsin and the other mechanisms we've gotta do, okay?